We're going to start with our next presentation, creating an alternative power generation source that maximizes efficiency and redundancy. So next up, we have Ronnie Carroll of Basler Electric and Michael Brown of Light Tower Rentals. They will join us on the EGSA stage to discuss a challenge case study on a midstream company that required 100% backup for gas processing plant. This system was successfully paralleled to utility and took the entire plant load to approximately 18 to 20 seconds. They did this consistently with all generators starting and paralleling across 5 group breakers. So let's welcome to the stage Ronnie Carroll and Michael Brown.
Hey, Hal. Oh, there's a pointer. All right, thank you. Hey. So I guess it's us and Drew are standing in the way of fishing and golfing, so we will get going here. I know Charlie got the Rolling Stones. I'm not sure what we just had there, but I guess maybe next year get some exciting stuff going on. First off, I want to thank the EGSA for having us up to talk about this really cool project wrapped up at the end of last year. I'll tell you, while we do send our technicians to the George Raleigh schools, this is my first time. I'm a newbie to a conference, and I got to sit into 2 committee meetings yesterday, education and the D&D, and I'm extremely excited. The stuff that's going to come out of the TOC, the generator, the load banking certification program, and definitely technician recruitment tool that we heard about. I can't wait to see some of these things happen. So can't wait to contribute more to this association as much as we can. So just an overview real quick, creating an alternative generation source that maximizes efficiency and redundancy. I know alternative, people might be thinking some type of renewable, but this is actually a recip application. Real quick, I'm not sure how many of you folks know about Light Tower Rentals or LTR. Basically, we were an outfit that we started in 1994 in West Texas, providing site illumination. We've grown tremendously. We operate in all the major shale plays. We provide site illumination, tanks, pumps, diesel, natural gas generators, just about everything you need to support drilling, completion, and production of a well. We are primarily focused in the oil and gas space. That puts us in prime continuous applications 90% of the time. So that's what we're used to doing. Recently, we got into more of a permanent installed applications, which we have had a lot of fun doing. One of the things, one of the differentiators with us that we've found is natural gas generators, EPA certified natural gas engines running on well gas at the site. Typically we're there before utility. A lot of times we're there even if utility is available because it's usually cheaper for us to be there. When we talk about multiple fuel options, natural gas there at the well site, propane backup. If anybody's been paying attention to some of the high horsepower conferences, the virtual pipeline for LNG is definitely becoming more readily available, and I think we've got some units running on LNG in the Marcellus and Utica areas. Distributed generation, emergency response is becoming a big thing in Texas. We're going to talk about that. And grid edge strengthening. So in where we are, most of the time we have fields being developed at the end of civilization, if you will, where we've got long runs of distribution, and voltage and frequency instability is something that we experience a lot, and it's very tough on some of these advanced artificial lift systems, especially the ones that are on drives with an electrical, NESP probably 3 miles into the earth. So we got onto the project. Basically, we had a gas processing facility. This is a 200 cryogenic gas processing facility that's gathering gas from this entire field. And I'll tell you, we had plenty of room to put these generators. We were not worried about that. You can see the plant in the background and all the generators there. So the scope was to provide 8 megawatts of power generation, primarily to serve as backup power to the plant. Penciling the value proposition out on this one was pretty simple. If you're not moving gas, you're not making money. So the second piece of it is we had a customer that was very educated in some of the ancillary programs that ERCOT offered. And so we were going to have to be, to meet ERCOT's 10-minute ERS program, but not necessarily emergency response in the traditional way. This one was actually load resource. It used to be called LAR, now it's called load resource. And we were also going to have a seamless transfer between utility and generation so that when we did participate in these emergency response events, we didn't lose power. And then we had to accommodate the exporting of power through a separate power meter. I know that some folks peak shave and might have some arbitrage power that they send back. This is actually 8 megawatts bid into the real-time market around ERS activity. So we found it was to our advantage to have a third feeder there with a separate revenue meter. Schedule, almost 9 months with commissioning and testing. We wrapped up in November. Ronnie and I got to spend a lot of late nights in a dark MCC building together. Got to know each other pretty good. Design and solution, LTR, so this is the thing, the 23 units. While it makes a lot of sense today, it was conceptualized around us having this aggressive CapEx program in 2013 and 14 with the growth and what was happening with the price of oil and gas. And we ended up having some excess inventory, and most of it was natural gas because it had just revolutionized things in this space. All the customers wanted to go from diesel to natural gas. It was, just think about the cost savings to run on fuel at the well site. Some states were offering a tax exemption and royalty exemption if you were consuming that at the well site. And then the environmental impact of not hauling fuel out down these roads onto private property to fill units. So the decline in activity during the market left us with some excess inventory. I don't know if anybody read the news the last 18 months. Had money tied up in energy stocks. It's been tough. So while engaging with the client on this specific project, we had some units ready to go that we didn't have to issue a PO for, and certainly didn't have a long lead time on some big units. And when we proposed this multi-gen segmented bus system, and we talked about especially the demand start-stop functionality with spinning reserve, this really made a lot of sense. And so it was a win-win for both of us. So when we talk about challenges, there were several. Testing and commissioning, the generation system was extremely difficult because it coincided with the final assembly and commissioning of plant components. That's kind of a catch-22. It was nice to be in the design phase, especially of some of the switchgear and MCC building when we were getting ready to install this equipment. But commissioning it made it a lot more difficult. And while you would think that a plant processing that much gas, we would have plenty of gas to commission with, the plant was not in operation when we were ready to test. So navigating the interconnection process definitely delayed quite a bit of progress. We were not able to start bidding into the real-time market when we wanted to. It made up the impact costs to that local substation, some of the transmission protection that had to be installed. That made up almost all of the unexpected costs, and I think that's probably what most people will run into. I don't know how many folks in the room have executed an interconnection agreement and exported upwards to 10 megawatts, but it's not something that is consistent yet. There's not a process in place with some of these folks yet. And then overcoming the customer's reluctance to forego traditional PLC control and use a genset controller. So I'm fixing to pass it to Ronnie. Ronnie was a true business partner to us in this installation, and I'll tell you, we had talked about using a genset controller on key switchgear, and then this was finally, we all come to these things, and we meet each other, and we talk about all this stuff, and we had this idea, and we finally had an idea, or a chance to make it a reality, so we were excited to do that. So I'm going to pass it on to Ronnie here. He's going to walk through some of the slides.
Thank you, Michael. I'm Ronnie Carroll with Basler Electric, and Like Michael said, when we first got approached, I had done a lot of training with those guys at Light Tower Rentals about the capabilities of their generators with the controllers that they had on them. And I kept telling them, if you get an opportunity like this, you want to go for it. The problem was not Light Tower Rentals, it was the switchgear builders and the contractors. They just insisted for months of the design process that they were going to use PLC to control everything. And I kept telling them over and over, and with Michael's help, we slowly turned their view. And even up till the week before we were going to commission, they still did not go with the group breaker controllers. So that was like the last straw. We kept telling them, okay, how are you going to control the generators and the group breakers to energize the large transformers with the groups? You know, I have to delay those closing to a dead bus until we have enough online to energize those 5 large transformers. And with that, and the engineers finally saw the light and said, okay, we'll put those in, and there's actually no PLC control from an external PLC in this entire system. And that was, I have to say, that was probably 2 months of meetings and phone calls and flights out to Dallas to talk these guys into it. I can say now that after the project was installed and we tested it, they were very happy with what they have. And I'm pretty sure that builder, that switchgear builder, if they have the opportunity in the future, they're going to use controllers like this instead of going with the PLC option. So the biggest part of this was the Basler DGC 2020 HD controller and our segmented bus capabilities. This is all built into the controller, so it made it really easy. The disadvantage with using that is that our normal functions for the mains fail functions and stuff like that don't work. You have to do everything in the logic. So it made it a little harder for me and a lot easier for the PLC guys. It also enabled us to do remote and local control and monitoring over Modbus TCP. And that was a big advantage. We also set up the demand start and stop functions to optimize fuel efficiency and ensuring enough capacity is online. Now, since this was a new plant, we did have a couple of days where we had to do some testing, and load started while we were setting, we tried to set our demand spinning reserve as low as possible to optimize fuel efficiency, and that kind of bit us a couple of nights. So we now have it set, I think, at a level since January. There's been no issues. No. They're pretty happy with what they got. So as the generators run, if they run for a long time, every 24 hours they'll rotate. And as loads start and stop, they'll add load to keep that spinning reserve. We also minimize the wiring between the controllers. So if you remember in the pictures we showed earlier, some of these generators are about 300 to 400 feet from the first set of bus tie breakers. And all of that interconnection, everything, all the status signals, everything we have is sent over the Ethernet using a distributed broadcast logic bits. And in the best logic in the 2020 HD, we have 128 bits available, so it made it really easy to set this up. We can send the status of every element to every other DGC in the system. And whether or not that DGC needs to read that element or not is up to the system design. But it's there in case there's any changes they want to do later down the field, we can easily do that. Our Best Logic Plus really makes it easy to do this. It's simple drag and drop logic. We can document the program as we do it, and that allows someone that comes behind myself or one of his technicians, they can see in the logic why we built the specific part of that logic and what it should be doing. And we can also do an offline simulator, and this really helped on site before we actually push the button to start the generators and close the breakers. We could simulate a lot of this before we actually put any power to any breakers and make sure that everything's going to work. Now with that, I will say, when you're doing a large system like that, as Michael said, we had a lot of things that slowed us down, a lot of things that stopped work. And good thing to say is it was not the controllers, it was all the auxiliary stuff, pilot relays, the customer not understanding where the connections should be made in the system, communications issues with the different types of communications that are used in the system, and more importantly, gas pressure. That was about a 2-week deal with that plant, as Michael said, produces its own gas, but there's also another gas supply to the plant. So if they're ever down completely, they should be able to run off of that. And there was issues with the piping, and as you can imagine, these are 23 natural gas units. Natural gas units are really slow to start, and you got to have large volumes of gas for this. And what size is that pipe?
6 inch.
6. And so they had a few issues with that, a few issues with the regulators, but once all of that was resolved, everything seemed to start working out. So the system here is a one line of the segmented bus system, and it basically means that we can take any set of generators and provide power to any other side with tie breakers. In this case, it's pretty simple. We have the 5 groups of generators going to one bus, and then that bus can either provide through one breaker to export for the grid support, or through another breaker to provide power to the plant, or to for a black start to the plant. We can open the utility breakers. And these broadcast logic bits really helped in the design of this, and I know this allowed us to not use interconnections between controllers with a lot of different cables, and it really made it easier. This was another selling point to the switchgear builders and the contractor, that they didn't have to pull a lot of wiring between the controllers, because 3 of the main controllers are all located about 400 feet away from the generators. So it would have been an extremely long run and a lot of cables to do statuses between breakers, which we really need in this system. So in this case, we can send all of the generator breaker statuses and all the group breaker statuses to the main controller, which is the main utility breaker controller, is the one we put the main set of logic in that we're going to use. And we had 3 modes of operation that the customer asked for. The most important one being the black start, because they want a standby generation. So the black start, we don't actually start the generators. We don't sense the utility fail and start the generators, which is a normal operation for our controllers. So what we do is they have a DAV, that's basically a PLC monitoring the plant status.
Oh, the Delta V.
The Delta V. So we send Modbus signals to that. We sense the bus failure on the utility side, whether it's through the 81 Rokoff or the 78, or it just goes dead, unstable. We send that status to the Delta V. The Delta V returns us a black start command, which we could have done all that, but that leaves them, and let the switchgear builders think that they have some control in it. And it kind of alleviated some tension that they were controlling what was actually when we were starting and stopping. We also have load takeover, and this is probably one of the bigger uses of the generators, is either locally or remotely, they can start the generators, bring them online, take the plant offline. So it's a peak shave, but not a true peak shave, because we actually disconnect from the utility and run the plant offline. And then they can control that from Kansas City as the...
That's Kansas City or locally, and along with the peak shaving, obviously we're capturing that 4CP avoidance, which is pretty big.
So that's the EPA regulation side.
4CP is the 4 coincidental peaks. It's basically what your rates are dictated for the next year.
That's right.
So we don't want to be using very much power on those days. So
it is a peak shave, but not a true peak shave, where we monitor. We can monitor and maintain a load against the utility that would keep them from reaching that level. But they did not want to do any parallel to utility across that one tiebreaker to the utility at the plant because it's not metered. And the other operation of this plant is metered export for grid support, as Michael talked about. And the other breaker has a meter on it, a power meter, and it's in reverse order. It's going to read the plant power out to the system. And it's kind of weird because this goes out and connects about 4 poles down and comes right back into the plant if it needs it. Some of that would, if we're fully at 8 megawatts, we would probably have about 3 megawatts going out into the system. The rest would come back to the plant. But for the way they have this set up, it's you're selling power back to the utility, and you're having to pay for gas to run the generator. So there's a whole who's paying for what and how it's going out. And I let those guys handle that side. I just helped them set it all up, make it work. Some more logic of how we did mode calculations of which one we're going to do. We had to know when the gen breakers were closed and to allow us to go into whichever mode we were going to go into. And then we can do the breaker statuses for the group breakers. And one issue we found with these group breakers, I typically do a system and we recommend station batteries as the power to the breakers. Because if you have no power, you can't open or close breakers. These are not that way, they're AC powered. So we ran into some issues immediately upon our first testing where the group breakers never opened because we shut the generators down first. So there was some back and forth figuring out what was going on. So we put time delays in the generator stop. They will not stop until all the group breakers open. And then they'll stop. So that allows us to have that because the power for the breakers is on the generator side. And then in our tiebreaker control, and this is the main tiebreaker, this is only part of the logic. I know it looks really complicated, but it's not. But we were able to allow for an 86 input from the relays, so we do have protection. We're using BE111s and SEL 751s to protect the utility side. So we use that. We make sure that we have all the breaker statuses, and they wanted different statuses in their PLC to know when we were doing certain things. Like if sync went active before the generator shut down, or after the generator shut down, they were getting an 81 trip. So I had to put some logic in to prevent that. That's what shows the versatility of the logic and the power of this logic really helped us do anything they wanted to do, we were able to do. And this type of logic and this type of control in the controllers now is really changing the way we do parallel systems. When the company approached us and wanted to do a test in Dallas with the 23 generators, Michael and his company was able to set them up. We had a couple of transformers. At that time, we used liquid propane with liquid withdrawal for the system, and we tested all 23 generators for those guys. And their interpretation was that with a parallel system, 23 generators, it's going to take 10 to 20 minutes to get them online. And I kind of chuckled, and I said, oh, really? So we set the system up, and they came out, and I think first time, 16 seconds, they were all online, something like that. So they called the corporate headquarters back in Kansas City, and they said, oh, that can't be right. There's no way. So they made them FaceTime with their iPad and watch the test, and I think second test right at the same time, 17, 18 seconds. So I think that kind of changed the way they were going to do this and offer it to ERCOT for how
we thought we'd qualify for spending reserve, but ended up not being able to. But either way, it's remarkable. These little engines are very nimble, and they start and close fast.
So some more pictures of the final installation. at some point there's going to be gravel around that because in the rainy season it's messy. During testing, once we worked out all of the bugs that we had with the gas and the pilot relays and the breaker settings, the relay settings, protective relay settings, and communications, we were able to do testing for peak shave. With the plant at 7 megawatts, all 23 generators are close to the plant and consistently in 17 seconds. All modes of operation were tested locally and from the remote location using the Modbus. And I think they were pretty amazed at how smooth that worked. There's a local HMI that you can see the status change from the Kansas City location. The generators start all online. Mm-hmm. And when we commissioned, we obviously didn't have enough plant load during startup, so we brought in 2 5-megawatt medium voltage resistive load banks to assist with this. And that's when we discovered as we were running our spinning reserve levels, that really helped to set the levels. Because as we were spinning reserve, they started loads that they weren't supposed to start, and we found out we didn't have enough spinning reserve. So, Michael?
Yeah, so basically going into that, we had the cut sheet, and the engineers we had looked at the largest load steps that we could incur while powering the plant. While this is a very state-of-the-art facility, every motor load is on a drive. We still ran into not having enough spinning reserve, so we had to make that change. Just to wrap things up, after overcoming the challenges with the interconnection and testing during final assembly, the customer has a completely operational system. This is a backup generator system that is currently generating revenue. All the requests made by the customer were accomplished in part by utilizing technology available out of the box with these controllers, and it's one of the things that I think all the controller manufacturers are going to. It's remarkable. And so at the end of the day, we've got a customer who challenged the status quo of buying a bunch of iron and having it sit next to the plant and operate here or there and hope it starts when they have a blackout, to exercising that equipment, which it likes to do against load, to make money. And they've taken control of their power security and the way that they buy power. So that's about it. And so this is the part where we ask for questions.
If you got a question, please raise your hand.
I assume those are PSI natural gas engines?
Yes, sir. Yes, sir.
Now, would that be an EPA certified prime stamp on an engine, or would that be a standard standby type?
No,
in the
that's
eyes of EPA.
That's a prime stamp, and we also had to site certify these engines.
So those are EPA prime. All right, thanks.
Yes, sir.
Two questions. So what is the redundancy level? I saw 2 utilities, 23 generators. What's need plus?
So this specific plant, we're 100% for the plant. This particular plant has 4 5,000 horsepower compressors on the residue side that use a technology that's basically dual drive. So they have a gas engine and electric motor. So they get those off of utility a little bit differently than we would have done it.
So I didn't see any transformers. So you're generating at 480 and then stepping up?
No, we step up to 1247. I think if I can go back to way back, not too far back.
Right there.
Here we go. So each group, each segmented bus has its own 2500 kVA transformer, and then arc flash calculations decided that we were going to have these group breakers, which we ended up needing for the to energize those transformers.
And then in the DD yesterday, we're talking about the next meeting of cybersecurity. So are the Russians online with this plant?
So that's a great question. I guess leading into what we're going to do, I guess what we're going to have is cybersecurity. So all these generators that are being installed all over the country are talking to each other over the Ethernet. over the local network. And we love to get in and access that remote network from other places if we want to troubleshoot or see what's going on, right? In this particular instance, the plant, most folks that are transporting natural gas or oil or anything down a pipeline, they're subject to DOT regulations. And they're extremely strict when it comes to cybersecurity. So the energy manager here is behind the firewall of the customer, the customer that operates the plant, and nobody has any access except for them. So it's a pretty tight, managed network. Much more than I can talk to because I'm not an IT guy, but I know it's pretty extensive.
Michael, based on the negotiated utility rates that the customer has, is there any estimated time for the system payback to the customer?
We do have an hour. It's tough to answer that question because there are some variables that you can only look at a backcast for. So we can't project what kind of revenues we could generate from bidding into the market. But based on LR and a few other things, I think it was less than 5 years. Just base. There's some economy to scale with that. I mean, if you were going to set a 400 kW generator there and try to participate in some of the programs ERCOT offers, certainly they're not going to pay as much.
With the given distance, what was the solution for network communication, and how was that communication secured?
Everything, let me see if I got a picture of that. So everything, as far as the 23 units and the 5 group breaker controllers, those were all copper Ethernet into an industrial Cisco network switch that converted it to fiber, and we went underground fiber into the MCC building. And then from there, everything was fiber. So the only copper we had was out here at the site. I think 300 feet after that, you need to go fiber. So we ended up having to do that there, which is nice. Nice functionality to be able to go back and forth with these controllers.
Hi, thanks for the presentation. Just wondering, how are you playing into the ERCOT market? Is it day ahead bidding, or is it just time of use offsets?
So there's day ahead. When you look at the LR program versus ERS, I mean, ERS, you're looking at a quarterly rate, and then with ERS, or a load, it's day ahead. So some of that stuff you just have to leave up to the energy manager and cross your fingers.
What type of utility protective relaying was utilized, or required, I should say?
What they dictated?
Yeah. I know for Basler we put in B111s, and there were also SEL 751s. I don't know about the settings on those, but the B111s interface with the 2 utility tie breakers as sync checks, and they were doing the 81 functions and the 78 functions. The other functions protection on that side. We did not set any of that protection in the HD itself. We did. We set those as the pre-alarms, but everything else was done with the relays.
When speaking about the demand start stop, you said the units rotate. What are you achieving by that?
Well, under normal demand start stop with either per unit load or in this case spinning reserve, if they run for 24 hours, we have them set for the units with the least number of hours should be online. So every 24 hours, they'll rotate as many units as they can automatically. The controllers that do this, start the other units, bring them online, and shut down the units with the most hours while maintaining the plant load and the spinning reserve.
Yeah, they exercise really well.
How much extra power do you have there?
Depends on the load, 3 megawatts maybe.
Yeah, probably so. I mean, they estimate this plant at 8 megawatts. You know, I've not seen it over 5 at 3/4 capacity. So we haven't seen a winner. We haven't seen the heat trace. So we'll find out. Those were procured by the electrical contractor, the engineering firm that we had do this work for us. I'm not sure who put those together. I think they were out of Houston. Can't remember the name.
Was it Prime?
Oh, it was Prime.
Prime Power.
Yeah, it was Prime.
All right, thank you guys for your time.